Hello, everyone. Welcome to Wind Down Friday. Today, our guest is Vladimir Odnoblyudov, CTO of Qromis. Hi, Vladimir. Welcome aboard. How is it going?
Hello, Maurizio. Yeah, thanks for the opportunity.
Thanks a lot for your time. So, where are you located, Vlad?
We're located in Silicon Valley, California. So the company is in Santa Clara. So that's where I making today's recording from.
Thank you. Good. Thanks a lot for your time. So, I have prepared a couple of questions for this new episode of Wind Down Friday. So, the first question is about your background. So, you have an impressive background spanning optoelectronics, semiconductors, executive leaderships as well. So, can you take us through your journey? So, how has your path evolved over the years?
Yes, thanks, Maurizio. Yeah, it's been an interesting, the career or road for me. I actually started back in St. Petersburg, Russia. Graduated from St. Petersburg State Technical University with a master's degree in solid state physics. And then at the same time, while studying at the university, I started to work at YOFI, Physical Technical Institute, which was right across the road. It's quite famous institutions. And I ended up in laboratory of Jores Alferov, who was a Nobel Prize winner in physics in 2000 for invention of semiconductor heterostructures. So that was great time. So I basically would study the classes at the university and then head down to the lab and do the work with the amazing team of, distinguished scientists there. During those years, I was working on laser technology, basically indium gallium arsenide, quantum well, and quantum dot lasers for 1.3 micron telecommunications. So at that time was, of course, a huge hot topic. So I really enjoyed it. I did MBE growth and then some fabrication and testing aspects of the lasers, and basically fell in love with semiconductors during that time. After completing that master's degree in early 2000s, I moved to or entered the PhD program at University of California, San Diego, and that program was in electrical engineering. So while at UCSD, I continued to work on optoelectronic devices, but I switched to LED technology. And basically did the same type of work, MBE growth, and then fabrication characterization of LEDs. Early on, I was very interested in commercial aspects of different technologies developed in the labs and how they could make it into commercial products. And then I realized within our group that that work which we were doing during my PhD was actually or had a good commercial potential. So after completing that PhD, went on to found a startup company called Quanlight, which was focused on developing that new LED technology. We did some great work. Some of our investors included Applied Materials at that time. So out of grad school, it was very nice, great progress. And then ultimately to Quanlight, and later on, towards the later years of that company, I met Dr. Jem Basseri, with whom, we continued to work throughout many years since then. And he was at that time with Micron technology, and Micron was entering a wide bandgap semiconductor field. So it was basically looking for a core team to start the program. And so I, later on transitioned and joined with Dr. Basseri, with Jem, to Micron. And we've been, kind of working together ever since. Micron and then together we went on to found Qromis. So Qromis is already 10 years, the anniversary we celebrated last month. So it was a big milestone. And that's where we are today. So with the Qromis.
Thank you. Thank you, Vlad, for sharing. A big hello
Thank you.
to Sam, your CEO of Qromis, your company. So, Vlad, of course, when we are talking about the challenges, innovation often comes with challenges. So, what has been one of the most complex technical or strategic obstacles that you faced in your career during your current job at Qromis. So how did you overcome it?
Yeah, so actually, I will take us back to early Micron days because that's where I feel like throughout my career, that was definitely the biggest technical challenge or innovation challenge which I faced and our team faced. Because at that time, and it was again like mid 2000s, so we were tasked with developing a new GaN technology in X memory fab because Micron was transitioning to 300 millimeter for its memory technology, so 200 millimeter fabs were available. And then we had to develop that new wide bandgap technology in that X memory fab, which would be scalable to 300 millimeter in the future, applicable to different markets. So basically covering the entire space from power to LED, including RF, and at the same time be fitting with CMOS fabs, be cost efficient, scalable, and have solid roadmap for the decades to come. So at that time, it was a huge technical challenge. So first of all, there were no even 200 millimeter GaN epi MOCVD reactors really available at that time. So because everything, of course, starts with epi growth. So we had to build our own epi reactor to start with before the commercial platforms became available for 200 millimeter. And then, of course, the substrate choice was a big issue, with usual suspects such as, sapphire, silicon carbide, silicon on the table. So we screened all those platforms. And then because of the compatibility issue with CMOS fab and also availability of that, the large diameter required for that fab, we of course ended up with silicon. But our confidence was pretty low, around 30% that this type of program could really result in, achieving of all the goals which we were faced with from the executive management because of well-known issues with, the GaN silicon, like we experienced wafer breakage, cracking, all kinds of, things which are customary to GaN silicon platform. So at the same time, pressure mounted from the management to deliver product and technology with the massive investments which they were doing. So we kind of stripped it all back down and started to look at the core issues and how can we address that. And that's where the innovation of engineered substrate came from. Of course, GaN and silicon, they don't like each other. Neither CT match or lattice match are there. So we looked at the core of that material science and came up basically that resulted in the innovation of this engineered substrate solution. So once we decided to pursue that, within 6 months, we had the first large diameter, fully integrated, CMOS compatible engineered substrate ready. And that completely opened up the program. It was actually quite amazing. The first epi tests which were done resulted in like 10 micron thick GaN epitaxy, no cracking, no breakage. The brightness of the LED, which we were doing at the time, went up by a factor of 10 just by switching the substrate platform because the defects were lower. And of course, the LED was a validation mechanism because at that time, there were no other commercial GaN devices in the market. There were no real power products. Again, it was like end of 2000s, 2008, 2009. So we had to choose how to compare the platform, and the device was, the LED, which had a commercial, the reference point in the market. So that's how we validated the platform, and within about 18 months, we had a top-tier performance and brightness LED on a new substrate platform. So that was quite remarkable. And I think to date, that engineered substrate, or now we call it QST, it remains the world's only commercial semi-spec CMOS fab friendly, the engineered substrate for GaN. And here also I'd like to emphasize that the strategic and double down investment approach by Micron senior management at the time, because they were really able and willing to take calculated risk with, strong investment and believe in the team, and that brought the big reward. And the speed of the development was amazing. So I always kind of remember those days with fondness. So
Great.
that's what I say was, probably the biggest turning point or the biggest technical challenge which we were able to overcome, of course, with all the team members at that time.
Thank you. Thank you for sharing. So, Vlad, and let's talk GAN. So GAN has revolutionized, is revolutionizing industries from power, not only power electronics, but also RF, optoelectronics. So based on your experience, so where do you see the next breakthrough for GAN technology? What challenges still need to be addressed? So if we are talking about power electronics, I mean, so do you see a competition with the other wideband gaps in byte?
Yeah, that's a great discussion topic, and I'm sure many community members would have different opinions or, various opinions, which is great for healthy conversation. But as much as we like GAN overall, and as much as it feels like that GAN has been around for a long time, in fact, it's a very young technology. If you just look at especially in the power side, right? If you look at the available product lineup, so most of the companies are on their first generation of GaN technology, and the product has been only around for a few years. With maybe a few companies who are already going to like second generation or introducing the second generation, and also on limited diameter platforms. So compare that to silicon carbide or silicon, which of course multiple generations ahead of GaN in that regard. So there is much work to be done, lots of work to do in GaN, and I think that where the community would benefit the most, or where the next breakthrough may come, is from more systematic studies within the industry and comparing different solutions and different platforms side by side, instead of picking one path and kind of following it all the way, continuing screening the different platforms or technologies which become available in a systematic fashion. So one example I could give is, for example, dislocation density in GaN, right? So there is still no systematic industrial level study from the real fabs. How does those dislocation density affect the device performance and reliability? So of course we hear many complaints that GaN is not as reliable or it's hard to qualify. But there is not enough effort probably still in, looking at the material quality or what impact it has on the actual device performance. So that's where I think the big opportunity is to continue, and also accelerating the cycle times and learning cycle in the big companies. So those type of studies probably would need to come from large IDMs who are driving the market, IDMs or the largest foundries also, but more so probably IDMs. But still the cycle times are pretty slow. Like if you compare power industry to say memory or logic or now AI, you would be looking at multiple months of cycle time for, let's say, one device slot in the industry. So that's definitely not close to what it's in the more conventional semiconductor markets. Like, again, I keep going back to but that example, with Micron, who is at the core is the memory company, the cycle time around the device was around 10 days and hundreds of wafers per week type run rate just for the development to validation. So that's speed and the resources and approach for screening multiple solutions at the same time. I think that would bring many opportunities and open up new avenues for GaN or new products too. In addition, further application work by big IDMs or tier ones is needed. Studying GaN versus silicon carbide in specific applications, because those are, of course, different devices. And it's not a secret that application needs to be completely redesigned.
Mm.
What's the right architecture? What's the right topology for this device or for GaN device or for silicon carbide device versus silicon? So that's still, a good chunk of work to do to continue, the advancement of adoption. In terms of competition with silicon carbide, so first of all, of course, GaN and silicon carbide is like apple and orange, although they both wide bandgap, but very different materials, different figures of merit, different cost structure, different scalability. So from that perspective, they are both great materials. So I think ultimately they will coexist, but there would be certain application where they would compete. That's inevitable. I think a good point would be that silicon carbide has about 10-year head start in commercial applications, compared to GaN. But GaN is quickly catching up. So in certain applications, yes, there would be a competition, but it would really depend on each specific um, the solution or the IDM who would show, how that particular application works and the choice which would be made.
Thank you. Let's do a break in terms of technology. So, as the
Mhm.
philosophy of wind down Friday, outside of work. So, what are your hobbies, passions? So, do you find any parallels between your hobbies and your approach to problem solving in technology, for example? So, tell us more.
Yeah, so having raised two boys, my hobbies are mostly around the sports, actually. I mean, I like sports through my entire life. I did different sports. I enjoy tennis, golf, swimming,
Nice.
also weightlifting. And those, the
Okay.
sports definitely help with daily stress. As you know, we all under quite a bit of different stress and the environment and always chase, but uh, finding time to do
Mm-hmm.
sports is definitely
It's
helping,
important.
and it's important, and there are good parallels with our professional work, of course, because it teaches you to, set the goals, achieve the goals, maintain, measure your efforts, and basically staying healthy. So from that perspective, I think the interesting point is that I probably enjoy more individual sports, although in professional career, I always enjoyed working in within great teams and really appreciate all the teamwork efforts,
Good.
which make the most impact usually on the project. So there's good teamwork effort, but maybe that's how I balance things out. So I'm like an individual sports side versus in professional career, it's more of a team effort. Yeah.
Thank you. Nice, Vlad. Nice. So, you have led both startups and large-scale corporate R&D initiatives. So, if you would give a suggestion and advice, so what advice would you give to engineers, young people looking to make, or at least to try, to make an impact, a real impact in GaN, but also other fields. So also others are
Mhm.
investing in other wide bandgap materials. So let's think about ultra wide bandgap, for
Mhm.
example. So which is your advice?
Yeah, so starting maybe specifically with GaN again, I will reiterate that it's still young technology and there is lots of things which could
Yeah.
be done from different integration circuits to application specific devices to vertical devices, integration with CMOS, co-packaging, uh, different backend technologies which have not been fully utilized yet, like TSVs, etc. It's just a lot to do. But in terms of execution or making, those ideas a reality, or the new type of companies, new startups, I would say that again, from my experience, the choice of the development platform is very, very important because if you not choosing the right one, not
Mhm.
scalable or costly, that would have a big impact, both on development and then ultimately on the product side. So that would be number one, the choice of the platform on which you're doing, the development. Number two, I would say that during the development, staying focused on the core technology or core product is very important for startup. In many cases, it's easy to get distracted. We can do that, we can do this also, and then the effort kind of spreads and that focus being lost. So just need to believe and stay focused really on your one technology, one core technology, one product. So that would help to kind of slice through the resistance in the market and, the penetrate. That's number two. And number three, I would say on the commercial side is making sure that the solutions which are being developed is not only applicable or could be realized with IDMs, but also with the foundries. Because that, getting the solution through the foundry or into a foundry is the ultimate path to full scale and, the further commercial growth. In terms of other materials, me being also, of course, partially from the material science world, I love all the new materials or technologies which are coming from gallium oxide, aluminum nitride, diamond, even the others. Lots of great work going on, and there would be different devices demonstrated. I think those are all healthy, and of course, there needs to be a roadmap. But the important thing would be to how do we scale those materials? So there could be a commercial aspect or commercial products made. It's still very hard to make a competitive commercial product, especially in power electronics, which is on very small diameter, right? Is it a coupon or 1 inch or 2 inch? So I think a lot of focus needs to be put into how to scale cost efficiently that platform so it can actually be run in more like mainstream type fabs, so it can be a commercial solution. But technology-wise, of course, like all those need to be studied, universities, labs, even certain maybe startup companies. Step by step, they would grow and also become more available. So.
Thank you, Vlad. So I have the last one before ending this great wind down Friday with you. So in conclusion, if you could take a conversation, could sit down for a conversation with any scientist, innovator, historical figure, past or present, so who would it be and why?
Yeah, that's a very interesting question. Of course, we're a substrate company, right? So that's at the very, very bottom of the semiconductor supply chain, right? Really at the bottom. So if I were to pick, different figures, I wouldn't pick probably one. Maybe I would pick a few, but I would probably try to reach all the way to the system level, the innovators, or to make the actual public-facing products or the final products, which going into the systems, right? And those would include, the data centers, EVs, consumer devices. So the great example of innovators there, or the visionaries, of course, would be people like Jensen Huang, Elon Musk, Tim Cook, or Jeff Bezos, who kind of commercialized all that front level or the top level where our power solution can penetrate and make the biggest impact. So I would definitely would like to have different types of conversation with the people of that caliber to basically explain how we enable all the way from the bottom, or how we can help the community through that commercializing or advancing the GaN power solutions and make it more accessible, better performance, how that can impact all the way to that level of the final system design of the products we see in basically in the daily life. So those would be my choice.
Good. Thank you, Vlad. Thanks a lot for your time. Thank you for this great conversation. I wish you a nice weekend, and so see you in some power electronics conferences, and take care. See you next. Thank you, Vlad.
Thanks, Maurizio. Yeah, thanks for the opportunity.
Thank you.
Bye-bye.
Bye.
Thank you. Bye.